Alright, now that I got your attention, let's talk about this new coronavirus, also known as SARS-CoV-2, also known as the virus responsible for your recent change in lifestyle. For things to go back to as they were, the spread of the virus must be reduced. We are all practicing social distancing, and that is a great way to alleviate the spread of SARS-CoV-2. But to accelerate the decline of COVID-19 cases, additive measures are crucial. Finding a new cure through experimentation is too lengthy of a process. This is why repurposing drugs that are already known and have been thoroughly researched is the more practical option. Before we dive into how these drugs will work against SARS-CoV-2, we must first understand how the virus works against us. For the purposes of this video, I won't go too in-depth in the structure of the virus, but what you need to know is that the coronavirus is spherical, has spike proteins, and genetic material stored within itself as single-stranded RNA. This makes sense as it is much more infectious. After binding to the ACE2 receptor, the virus is pulled into the host cell through endocytosis, which forms an endosome. The endosome then fuses with the lysosome, forming an endolysosome. The virus will now be uncoated by lysosomal proteases, making the RNA transcript available for replication and translation. The RNA transcript is replicated by RDRP, RNA-dependent RNA polymerase. After replication, the RNA transcripts are then translated by ribosomes to form the proteins necessary to build the virus, such as spike proteins, envelope proteins, membrane proteins, and other proteins. The membrane protein is currently known to be involved in the assembly of these proteins by directing these proteins to the endoplasmic reticulum for assembly. After this, the Golgi apparatus will package the assembled virus into a vesicle so it is able to leave the cell. This process will repeat until it is time for the virus to leave the host cell and infect other cells. Once released, the virus will go on to infect other cells in the body that have the ACE2 receptor. Many of these receptors are located in the lungs, which is why COVID-19 has severe complications for gas exchange. Now that we know how SARS-CoV-2 attacks us, we have the information needed to understand how it can be stopped. Chloroquine is a weak-based drug which is able to elevate the pH of acidic intracellular organelles. This is especially useful against the coronaviruses. In regular conditions, the virus will enter the cellular membrane through an endosome. However, when chloroquine is present, the endosomal pH is raised and not suitable for the virus, therefore it cannot gain entry into the cell. Without chloroquine, the Golgi apparatus would package the virus into a vesicle, allowing it to leave the cellular membrane and infect other cells. The virus's structural proteins are assembled in the endoplasmic reticulum, but due to chloroquine raising the intracellular pH, the enzymes involved with assembly lose function. This interferes with the replication cycle of the virus. When chloroquine is present, the Golgi apparatus is unable to package the virus into a vesicle. Because of this, the virus is unable to leave the host cell and will not be able to infect other cells. Zinc by itself is unable to breach the cellular membrane because it is a charged ion. However, when chloroquine is present, it acts as an ionophore and allows zinc to pass through. Once zinc is across, it will bind to RDRP, making it unable to play its role in RNA replication. If the virus cannot replicate, then there will be no infection leading to COVID-19.